So I want to go back to the Druckrey-Kupfmuller equation that was on exam number 1. It's the kind of equation that those of you that are working on the imidacloprid toxicity project in the biolabs might be interested in an equation like this. Because again, the point of the Druckrey-Kupfmuller equation is that it's supposed to relate the dosage of some toxic substance that you expose an organism to the length of time that it takes that toxic substance to affect the organism. And those are defined in different ways. This is the paper that I looked at that inspired me to look at this equation as an example for this course. It's a paper from the Journal of Toxicology. And in it, there's the results of several other studies that investigate this dosage versus effect time relationship. And the one I want to sort of circle at this point is the data set that we're seeing right here, which is from a study in 2009 where they exposed Daphnia. Those are those little transparent water fleas that I think they might still use in some high school bio experiments from time to time. They exposed those fleas to imidacloprid and in varying dosages and figured out how long it took for that toxic substance to have an effect. And the effect that they decided to define was that they wanted to figure out how long it took half of the fleas that were exposed to that substance to perish. And so here is this data set. So what if my question to you were, how can we investigate whether the Druckrey-Kupfmuller equation, which is over here, this is a relationship between D and T, how can we linearize that equation to investigate the relationship that we're seeing in this data? In particular, let's keep in mind what are the variables and what are the parameters in the Druckrey-Kupfmuller equation. First of all, what are the variables that we're interested in here? The two quantities that we're trying to relate together are the dosage and the time, the effect time. So those are the variables, D and T. Meanwhile, everything else in this equation, the n, which is just some exponent, and the k, those are parameters. And we don't know, at least in the beginning, we don't know what values n and k should have, but we should be able to get a suggestion for what values n and k have using this data. But before we can do that, if we want to use a linearized relationship to investigate the values of those parameters n and k, we first have to linearize the Druckrey-Kupfmuller equation. dt to the n is equal to k. And the group that's working on question K4 with the carrying capacity of a biological population, this question is kind of directed at you. When I linearize this equation, I'd like to do so in a way that will allow me to determine the values of n and k, and that I want the values of n and k to somehow be in my slope and intercept. So how should we linearize this equation, dt to the n equals k, in order to make it so that my n and my k belong to the slope and the intercept of the linearized equation? What should I do? What do I need to do, for sure? What's the big obstacle? Yeah, the big obstacle is that n is trapped up here in an exponent. So we need to rescue the n from the exponent insofar as we can. Well, what one tool do we have in our toolbox that can help us to rescue something which is trapped up in an exponent and bring it down? A log. Yep, a log is exactly what we need to get that n from an exponent down into a base. So let's take, all right, to rescue that n from the exponent, let's take a log on both sides. And when we take a log of both sides, we get to choose what base we want. We used base 10 earlier today. Let's just, for the sake of variety, use a natural log. So base e. Why not? So on the right-hand side now, I get the natural log of k. On the left-hand side, I have the natural log of d times t to the n. And what I'd like to do is, to the extent possible, try and rewrite that expression to make this look more like a linear equation. So what can I do? I have two operations happening inside of my log. I have multiplication, and I also have an exponent. So what should I do to simplify the expression in the natural log, given that I have multiplication and a power going on the inside? Let's handle the multiplication first, again, because we're trying to unwrap the n here, so we're running the order of operations backwards. Handle the multiplication, but multiplication inside of a log becomes what on the outside of a log? Addition. So when I break apart what's inside of my logarithm, I'm going to have the natural log of d plus the natural log of t to the n. And keep in mind that that t to the n is all inside of a log still. And on the right-hand side, I have natural log of k. Okay, but we still haven't rescued that n from the exponent. How do we do it? We can just slide it right out front. After all, taking a power on the inside of a log is the same as multiplying on the outside of a log. So that n we can just ship downstairs in front of the log and get n times natural log of t. And then we are all set. Natural log of d plus n times natural log of t is equal to natural log of k. And this is an equation where now nothing is trapped in the exponent anymore. Everything is down on the bottom line, down on the floor, if you like. And the only thing that probably as a scientist we'd want to do to this, if we wanted to make it look more like a linear equation, notice that our original variables that we were interested in, d and t, are on the same side of this equation, which doesn't make it look like y equals mx plus b very much. So what should I do to make it so that the d's and the t's are on opposite sides? Let's just take one of these terms and move it to the other side. Subtract it. Yeah. It's being added into the left-hand side, so let's subtract it from both sides. And what we'll get is on the left-hand side, we'll only have natural log of d remaining. And then we'll have equals. And when I subtract that term, the n will become minus n times the natural log of t, ln of t. And then our natural log of k will still be in the mix there. But that, because k is a constant parameter, remember, that natural log of k on the right-hand side is also a constant. So, to wrap this up, what are our linearized variables? What's playing the role of x? What's playing the role of y?
Y would be ln d.
Yep. Natural log of d, yep. And x?
Natural log of t.
Natural log of t. So in other words, if we wanted to investigate a linear relationship in the data that we've been given up here between d and t, what we should do is create a linearized plot where on the x-axis we use a logarithmic scale and on the y-axis we use a logarithmic scale. Natural log of t horizontally, natural log of d vertically. And now finally, what's the slope of this linearized relationship going to tell us? Slope is going to equal negative n. So if we want to know what the value of the exponent in the Druckrey-Kupfmuller equation model for this data is, if we want to know what n is, we should find the slope of this linear relationship, and the slope is going to be equal to the opposite of n. So if I find out that the slope is negative 12, then that must mean n is equal to 12. And then the intercept. Natural log of k. The intercept is an interesting idea in this equation. I guess it means the intercept would be the value of the natural log of d when the natural log of t is equal to 0. In other words, what would the dosage have to be in order to see an effect in 1 day? In other words, in order to kill, I guess, half of our Daphnia in 1 day, what would the natural log of the dosage need to be? So that's the question that the intercept would answer. The slope is maybe a little bit more interesting to the problem because the slope, probably and the intercept, are going to vary between different toxic substances, so between imidacloprid, thiacloprid, whatever else we decide to use. It might also vary between different insects. Some insects might be more susceptible to certain insecticides than others might. But this is how we can linearize this data to hopefully discover the values of these parameters. And so we just need to take the natural log of each of these numbers. Oops, natural log of that. So there are the natural logs of the t's. Let's take the natural logs of the d's as well. And now if we plot this data instead of the original, we should see something that helps to answer the question that we were looking at. So again, scatter plot with just the points. It's not the most fabulous linear relationship in the world, but it's at least it looks a little bit more linear than the one we were looking at before. Now we'll just add a trend line. Include the equation and the r-squared value. And then I'm just going to go in here and edit. So this was natural log of d on the y-axis. This was natural log of t on the x-axis. And what does it look like was the value of the exponent n that we were looking for? Remember that the slope, we decided, was the opposite of n. But what's the slope of this linear relationship? Negative 1.12. So what does that make n?
1.102.
Positive 1.1021. Yep. So we would conclude, based on the linear regression shown here from the data on the effect of imidacloprid on these Daphnia water fleas, that the exponent in the Druckrey-Kupfmuller equation that models this data is approximately 1.10.